Thank you all for coming today. We are so excited and so thrilled to be here today for so many reasons, one of which is this public widespread launch of nTop platform. My name is John Graham. I'll be the host and answering some questions, typing those in and moderating a little bit later. The other reason we're really excited today is because we have our very own Brad Rothenberg, the founder and CEO of nTopology, is here, and he's going to be talking in his own words and providing some background about the company and insight into how and why customers are using our solutions. After Brad comes on, we've got one of our talented lead application engineers, Jonathan Harris. He's going to show you some tangible examples from one of our customer case studies, and then we'll come back and answer some of your questions at the end. So without further ado, I want to introduce Bradley Rothenberg, our CEO. Brad, thanks for joining us today. Take it away.
Hey, John, thanks for the intro. And everybody who's joining today with us on the line, thank you guys for signing in. It's a really exciting day for us at nTop, and we're excited to kind of take you in more. And so, as John said, I'm the CEO, founder of nTopology. And, from day one, our mission was always to enable engineers to design and ship higher performing parts faster. And, what's interesting is we sit at this time where manufacturing is going through a huge paradigm shift. And any time in history where the way as humans that we make things evolves and changes and shifts, all of the business practices, all of the design tools, all of the ways that we actually make and design those parts has to evolve to take advantage of this new manufacturing technology. And really that shift has been to advanced manufacturing. Advanced manufacturing is the driver that's allowing us to kind of innovate on the new engineering process. And so what does advanced manufacturing bring to the game, right? You can make parts with unprecedented part complexity, things with complex lattice structures, designing the material properties, controlling the crystal structure of the material. There's never been a time where we were actually, not only are we designing the material of the part, but we're designing the shape of the part at the same time. And that's very different than traditional manufacturing. I would define advanced manufacturing as building directly from a 3D solid model. This is a paradigm of 3D models, not drawings. And so what is important in the process, right? We have knowledge capture and knowledge sharing. You want to take the work that your best engineer can do and deploy that across the company to leverage these complex parts that we can make. And so what else is advanced manufacturing bringing to the game, right? Now the performance of the parts that we can make has exceeded the capabilities of the current tools that we're using. And I'll kind of jump in ahead to kind of show where those limitations are. And with these new advanced manufacturing processes, automation is critical, right? We're dealing with these complex systems that, very, very hard to comprehend the, local material structure and crystal structure of material. So we need to automate the design of those processes. And so, if I jump into the problem in the space, and the problem with the current tool chain is that as engineers, we're wasting time on low value work. Things like, model cleanup, moving engineering knowledge into a CAD system, going from CAD to simulation, CAD to manufacturing, and then getting the final output. And, that's because CAD was built and designed in a time when drawings were the kind of way of doing business. And so, CAD was really great as a documentation tool, but it struggles when it's used for actual engineering. And the problem exists at the level of the data structure, the way we actually represent the part. And because 40 years ago when we started to build CAD, which is the centerpiece where the model lives, because drawings were the paradigm, all of the data structures that we use to represent those parts are really perfect for drawings, but they're not ideal for engineering. And that's why the data model in simulation actually differs from the data model in CAD and differs from the data model in manufacturing. And the CAD model itself really doesn't capture an actual solid. It's a collection of surfaces surrounding a hollow part. And so we really released nTop platform. We're releasing nTop platform today to address this problem, which is, the current tool chain does not allow you to innovate fast when developing workflows for advanced manufacturing. We've built nTop platform to really eliminate the non-value added work in your workflow. And so, the key capabilities for us in this, we're calling it a computational modeling platform. And the key capabilities for us is this new underlying data model that's higher performing and more robust. And the model itself, we call it a field-driven approach, because this new modeling technology that we built actually allows simulation engineers, design engineers, and manufacturing engineers to feed inputs into the same model. And so it really unifies these three processes. And then the other key component is reusable workflows. So a lot of the work that you're doing, because we have a more reliable model, that work is more reusable. So if I have a workflow for this, trailing edge bracket, for example, I can apply that same workflow to another bracket. And that's because the model is robust, and when I make changes to it, it updates and it doesn't fail. And so, from a workflow standpoint, when you use nTop platform, it's almost like you're authoring a workflow. It's almost like you're building a computer program, and that computer program allows you to define some inputs, a workflow in nTop platform, or multiple workflows tied together, and some outputs. And so those inputs could come from, CAD. We could bring in data from Creo, NX, CATIA, SolidWorks. Could come from engineering. So, you could pass in some simulation data, some data that you're measuring. It could also be process knowledge captured in the workflow. So things like, you might have a targeted scan strategy for how you move the laser across the powder bed to develop the best material properties. And so those all become inputs to the nTop workflow, which uses those to create and generate a higher performing part around that. And we'll show you a demo at the end of this. And what we output then are a few different things. One, we can output data that can go back into CAD or go back into your PLM for archival purposes of the part, or for documentation, like you still might need to make a drawing, for example. We can also output a model for simulation to validate your part. And we have our own internal simulation tools for stress and thermal, but we also have partners in the simulation space, ANSYS and Abacus, and we can go directly to them for validation. And then we can also output direct to manufacturing to our partners in the manufacturing space. So for right now, those are GE, EOS, Renishaw. And so what does that mean? No more STL. You can bypass going to a mesh and having to slice it. We can deal with the manufacturing setup directly in nTop. And I think, John, you have a poll question here. Do you want to throw that up on the screen for a second?
Yeah, you should be able to see that now. So another interesting distribution of who we have on the line, which is great to see. So Brad, I'll close this and send it back to you.
Great. And so, for us, the key enabling technology that allows for this is this new modeling technology that we have. And we could point you to our blog for some more background on the modeling technology, but the key here is the technology really enables interoperability and more reliable modeling, right? We could feed in CAD surfaces, meshes, volumetric meshes, the results from simulation, like your stress field. The way we represent the model allows us to pull in fields directly and drive parameters of the model. So things like these gear teeth could, the wall thickness could get thicker in certain areas where there's higher stresses. And then we can also output things like slices directly from the model. And we can model, arbitrarily complex structures like lattices, and which we'll show some more of later today. And so we know that, you're deploying nTopology platform next to existing tools, right? We're not saying we're going to replace your existing CAD tools, but you could use nTop to really solve the problems that the traditional tool chain has a really hard time solving. And so, like this big design study of heat exchanger coupons, and these are generated, in a matter of seconds. Our model could generate 200,000 different models, where a traditional CAD tool would have trouble generating one of these. And so this really allows you to explore the full design space of the parts that you're building. And something that's interesting to note that I like talking about here is the model itself. From a file size standpoint, you might be like, okay, 200,000 models, okay, I don't have 500 gigabytes of memory to store those. But actually, this model stored as an nTop document is actually lighter weight than the picture of the model in the program. The model itself is a matter of kilobytes, and this picture I think was like 64 kilobytes or something. And so I think that's amazing. And so, to show a couple of examples where customers are, producing high performance parts, first we have a set of satellite brackets that Zenith Technica is building. Zenith Technica, I would say they're arguably the best manufacturers working with RCAM machines. And so this was a large scale topology optimized bracket that was built for satellite applications. And essentially here, what's nice about this is you can set up the topology optimization process, and because our model can read in that field directly from the topology optimizer in nTop, we actually can automate the generation of the geometry. You don't have to go in and model all of these little beams. Now, there's also a process where you can validate the part afterwards. And in this model, the optimization was actually missing a few beams that, for reliability, the engineer who was working on this was like, oh, I want to add a couple of beams here. And so you're actually able, we call it flexible modeling, where you can actually add in additional structural members after the process, and they come in with nice rounds and nice blends very easily, and they always connect to one another. And so you can add in your engineering intuition on top of the optimization results to produce a higher performing, more robust design. And again, this goes directly to the machine to manufacture sliced, no STL. Another example is we have Tangible Solutions producing medical implants in nTopology platform. And when you're working on medical implants, a really important aspect here is what they call osseointegration, how a medical implant could integrate with the bone. And so Tangible is able to actually tune the material properties and the structural properties of these implants to produce a structure that has optimal osseointegration. And what's interesting here is, one, these, we call them trabecular structures. They were generated in real time. You can make a design change and see the structure update and see how the performance responds to that. And so, design optimization for performance is a win here. And then also this aspect of repeatable workflow. So once they tuned this model that can develop the perfect trabecular structure, they can apply it to their whole range of designs within a matter of minutes, because that workflow can be packaged and reused across the company. And so, there were, in this case, 4 distinct medical devices, all with distinct lattice designs, and they were all created from the same workflow in nTop platform that was reusable. And then for another exciting example, which Jonathan will kind of take you through after my presentation, is Cobra Arrow producing engine blocks in nTop platform. And I look at this as a really perfect example of a nTopology workflow where Cobra is not saying, hey, we're going to design this whole new assembly in nTop and use advanced manufacturing to 3D print the whole thing. They're actually like, hey, we're going to pick a part that makes sense for advanced manufacturing, which is this engine block, right? The engine block was a cast part previously, and as an engine block, which you can kind of see, through here in the center, that engine block, when it was cast, it had to be solid. Because it's 3D printed, you don't actually need to make it solid. And actually, the pressure in the cylinder is not so much that you need a giant brick of aluminum. And so now that they're making this part made of thin shell walls, they can actually fill it with a giant heat exchanger. And so, in this case, they went through a number of design iterations. There were multiple design variants of the engine block. The cylinder was changing in the process, where the exhaust was going. And what's really exciting here is actually that because this is hollow and filled with heat exchanger, the airflow actually now flows through the engine and cools around the cylinder. This was built by Renishaw on their new machine in aluminum, and it's also a much lighter weight part. And this is going to be shipping in their latest UAV. So this is an engine for an unmanned aerial vehicle. And they're also tying physics to the design process. Both aero and thermal models are driving the design intent. And so I'll leave it to Jonathan to show you exactly how that part was built. And thank you guys. And please, if you have questions, feel free to write them in, and we'll get back to you right after.
Great, thank you, Brad. So yeah, let me walk you through this this engine design here. So As Brad mentioned, this is really a great application of using nTop platform, where the designers at Cobra, they identified this part in this CAD assembly where they figured that advanced manufacturing could give them an advantage. And that part that we're talking about, that's in here, this blue one. So if I just hide this out here, you can see where that would reside. And so what they did with our software was take that remodeled casing, bring it into nTop, and then this is where we can do that advanced infill design. So the way the workflow was executed was one CAD import for this external part, one CAD import for this this internal region to fill, and then where the real power of the software comes in was the importing of various sources of data. So in this case, there were a whole bunch of different teams working on this aircraft engine, and they all had different data. And within every engineering process, there's the trove of useful data that can be used, but it's not only difficult just to process, but difficult to apply. And what nTop platform can do is synthesize data from multiple sources and apply them to a solid model. And so here what we had was a thermal field measured by the combustion team. That's imported to nTop. You can see that up here. A pressure field from the vehicle scale CFD model. So that's seeing where the flow off the vehicle is giving the most pressure into this cooling area of the engine core. And of course, the stress field associated with using a lattice. So if you've done additive manufacturing and applied a lattice infill, you'll know that in some regions of the lattice, it doesn't behave the same as it would in the core versus along the edges. And so what their stress team did was apply this simulation conducted in nTop to compensate for those lattice edge effects. And lastly, and I think most critically for this application, is that a vector field of velocity streamlines coming through this engine and around the core was imported so that we can orient our lattice and spatially vary it from one unit cell at the front, which promotes airflow, to a different unit cell at the core, which promotes thermal conductivity. And that's a unique capability of our software, and I can show you a bit more of how that works here. So if you're looking just to do a uniform infill, I mean that's really a one-click job in nTop. But as I mentioned with that slide, there's a lot more that you can do, and a unique capability is this spatially varying technology. So in this little core sample here, our engineer, they created this lattice through a series of tests to find that this unit cell type down here is better at airflow, and maybe this denser one with more cross beams is better for thermal conductivity. And what you can do, you can take this this material chart and apply it to any sort of vector field that we have. And in this case, we have a flow around a cylinder, and you can see how that orients not only to that flow field, but it also varies in unit cell type from left to right. Now, this file, this is just a little core sample, but the power of nTop is that you can have one engineer working on something detailed like this and just send it over to the other team member doing the part scale design. And so what we did was just import that file and apply it to this engine. And you can see how that orients on the vehicle scale around this cylinder here. So we have one unit cell type at the front, changing to a different unit cell type around the cylinder. And that's where we start our process of adding in these different sources of field data. So to start, I mean, we have the imported flow data, we have the imported thermal data, and we can use this to drive the density of the lattice. So we put more where there's more heat to conduct. We can lighten up the lattice where we need more airflow, and we can stiffen up the lattice where we need to compensate for these edge effects. And that's extremely easy in the software. I mean, you can see as I'm stepping through this that we can stiffen up the edges just in a click, and that's linking that field directly to a model variable, in this case, relative density. And so as I pass through this model, we can just do a quick section cut and show you how that lattice varies as you go through the engine. And so that's that sort of spatially varying lattice. That's how you can synthesize different engineering data sources into a model. But you can also do some pretty exciting conceptual design work, like using gyroids and various other cellular materials. So something like this could be definitely aesthetically pleasing for this application, and you could also do something like this to promote airflow as well. And you can see applying these infills is extremely fast, and as Brad mentioned in one of the slides, also extremely lightweight. This entire infill is probably on the order of tens of kilobytes, and the beauty there is how our software works at its core. That's our implicit kernel. Okay, so let me proceed down the workflow in this case. Now, of course, if you had this part, you'd probably want to go and use additive manufacturing here. And with our model, you can slice different areas of it independently. So something like this. We can slice the lattice. We can slice the outer casing. If I just hide the lattice for a sec, maybe we can apply a scan strategy unique to the outer casing, which we can see run very, very quickly. So now I have this hatching with stripes pattern on each of the layers for the outer casing, and then the lattice is exported at a different process parameter set. So you don't have to mesh this, which is quite a relief for anyone who's tried to make a part of this scale of complexity. These slice files can be read right into metal powder bed machines, and you can build from those directly. Of course, you could also use some supports here, and we can do that just as well. Now, in the engineering process, very rarely do you get to get off easily.
Jonathan here.
Oh,
Jonathan, this is the boss here. So we were actually looking at the engine, and as a design team, we decided that we need to move these valves around and replace it with multiple valves, and actually add a little V and change the design a little bit.
Oh no. Oh, can you send me the model? Is it this one? That's quite a big design.
Yep, that's the one. See all the different changes? We have 2 valves now instead of 1, and like some different.
Okay.
So guys, I just put the poll up on the screen for everyone that can't see your screen. Sorry if I jumped the gun there, but Brad and Jonathan are reenacting what a common scene is in many organizations. Unexpected design changes. They happen all the time. I think this is probably along the lines of what many of you were expecting and what we thought too. Oftentimes, it would probably be the average there that design changes are disruptive to your product development workflow. So guys, go ahead and keep taking it away.
So I think for the sake of this webinar, we'll go with always in this case. And the model change that we're talking about here is quite significant. I mean, if you were in a conventional CAD tool and you saw the model change from this to this, and you need a spatially variant infill, this would be a bad sign for you. But in nTop platform, what I walked through before was not the creation of just a part. It was actually the creation of a workflow, which you can reuse. So the model input was just that. It was an input. And you'll see as I change that here, this will run through and re-execute that entire workflow hands off. So what it's doing here, it's going to complete that infill. It's going to apply those data sources from 4 different sources, both 2 simulations run in nTop and 2 imported fields. And you can see that as this loading bar is going, we are getting towards that, that rebuilt part. And I mean, you can see it's remeshing this entire inner volume. We've got that, so we have an FEA quality mesh done there. This is going to rerun all the simulations and then give us a part. And so at this point, we're just rendering. All the execution, that's done. That was maybe 45 seconds or so. I can count the number of times I've spent 45 seconds just trying to find where my loft failed in a CAD tool. And here I've completely redone this workflow in about 3 clicks to this new geometry. And you can see that lattice that compensates for edge effects around this new barrier. So this is, I mean, a completely reusable workflow if you're working on a similar part like this. In CAD, this would be a big headache to redo all of this. But as you can see, in less than a minute, I've got my part. Now, one thing I would like to touch on again, which I skipped over, was that a lot of times, I know we had a few manufacturing engineers in the on the audience. A lot of times we have people develop very specific support structures for their additive manufacturing workflow. And in this case, it's no different. So we had our manufacturing engineer, Chase, he designed these support structures specifically for the material and machine that was being used and tested them on a variety of coupons. And you can see the detail of the teeth and the reliefs here. Now, this workflow here, this can be shared to the whole company. All you have to do is file save, go into the new file import, and then that that support structure block can be applied to any part, and it's specifically that that geometry. So if you dial in your process on a coupon scale part, you can share it with your whole team, and so you're connecting the whole engineering team together. So with that, that's the completion of the demo, John. I wonder if you have any additional poll questions.
That's all for poll questions. I kind of wish I had more.
Okay.
Those are fun. And I always know when I'm on webinars, I love filling those out and giving my opinion. But Jonathan, if you could jump back to the slides, just 1 or 2 more to show. If any of this is interesting to you, we encourage you, get in touch with us. If you would like a personalized demonstration, if you are a software or hardware vendor and think there is in some way we could be working together, if we could be doing something better together, contact us. We would love to hear from you. Also, we do have a blog. We love putting our thoughts out there, and please follow it, nTopology.com/blog. And also go to our website to look for future webinars like this. We'll try to have a regular cadence, having one every month or so. So that'll conclude the webinar today, everybody. Thank you so much for coming. We appreciate it. If we didn't answer your question, we will follow up with you individually as soon as we can. So thanks again, and have a great rest of your day.
Thank you guys for joining.
Thanks, everyone.